we're going to look at the energy of planets as they go around in an orbit. First off, we need to define a gravitational potential energy. The derivation for this involves calculus, so I'm not going to do it for you guys, but I'll just give you the formula. The gravitational potential energy is equal to minus G m1 m2 over r. So it looks kind of like the equation for gravitational force. Instead of the 1 over r squared, you have 1 over r, and there's this negative out in front of this. Now, we want to note that as r goes to infinity, the potential energy, as r gets bigger and bigger, the potential energy is getting closer and closer to 0. So what this means is, remember, for potential energy, you can set the 0 wherever you want to. For planetary orbits, however, it is conventional to say that the potential energy equals 0 when objects are an infinite distance apart. That's where potential energy is equal to 0. Now, for for planetary orbits, we know that gravitational force is a conservative force. Remember back at some point, I think the beginning of this semester, the third quarter, we talked about conservative and non-conservative forces. Conservative forces conserve the mechanical energy of the system. So since gravitational force is conservative, therefore that means that mechanical energy is conserved for a planetary orbit. So the first question that I would ask you, and as always with these video lectures, I recommend that you pause the video, think about it, answer it, and then continue with the video and play to see whether you are thinking correctly or whether you've gotten the correct answer if it's a numerical calculation. First question I want to ask you about is where in Earth's orbit is potential energy at a maximum? And we know Earth's orbit is not a circle, so the radius is not constant. Its distance from the sun is not constant. So where is that potential energy going to be at a maximum? Now, this formula is a little bit dangerous. When you're thinking qualitatively, not plugging in numbers, but thinking about how things change when stuff happens, you have to be careful because potential energy, it's over r. So as r gets bigger, this gets closer to 0. So your immediate inclination might be to say that as objects get farther apart, the potential energy decreases. However, this negative is also part of the formula. So note, as r increases, potential energy goes to 0. As r decreases, potential energy becomes a bigger negative. So even though the absolute value of the potential energy is getting bigger as r decreases, that actually means that the potential energy is decreasing. So where in Earth's orbit is the potential energy at a maximum? Well, as r increases, potential energy is becoming less negative, getting closer to 0. So as distance between them increases, potential energy increases, and vice versa. So where in the Earth's orbit is potential energy at a maximum? So PE is maximum at maximum R, and the maximum R is found, in case you don't remember the term, it is at aphelion, the farthest point from the sun. So then, by we can also then consider where in Earth's orbit is kinetic energy at a maximum. And what do we know? Well, we know mechanical energy is conserved, so kinetic energy is maximum where potential energy is at its minimum. And where is potential energy going to be at minimum? Well, potential energy is getting smaller as R gets smaller, so potential energy is at a minimum at perihelion, which is the closest point to the sun. We also talked about this, so this is a second way of explaining when planets' speed is greater or lesser. Planets move faster when they're closer to the sun and slower when they're farther away. Earlier on in the unit, we talked about how you could make that argument on the basis of Kepler's second law, and now we see that you can also make that argument on the basis of conservation of energy. So both principles are a way to argue about when the velocity is the greatest. And of course, if I ask you where in Earth's orbit is mechanical energy at maximum, think about that for a sec, pause if you need to. And that's kind of a trick question because we said up here, mechanical energy is conserved for orbit. So mechanical energy is constant for the orbit. So where is it at? So there is no maximum exactly, or I guess you could say it's at a maximum value for the whole orbit, depending on how you want to think about that. But point being that mechanical energy remains the same throughout the orbit. So potential energy is largest at aphelion, kinetic energy is maximum at perihelion, and mechanical energy is constant throughout the whole orbit. So let's take a look at doing some calculations. So let us say let's find Mr. P's gravitational potential energy at the top of Mount Everest. Okay, this is a simple plug and chug into the formula. Mount Everest is 8,848 meters above sea level. Mass of Parkhurst is about 85 kilograms. What else do we need? We'll look at the formula. M1, M2 are. Okay, so mass of Earth is about 5.97 times 10 to the 24th kilograms, and the radius of Earth is 6.37 times 10 to the 6th meters. So we know potential energy is minus G M1 M2 over R. So that's minus G 85 5.97 times 10 to the 24th. And R, remember, is the distance from the center. So in this case, the distance from the center of the Earth is going to be the radius of Earth plus the height of Mount Everest. And then we can plug numbers in and calculate what that value is. Don't forget to put parentheses around your denominator. So I've got G times 85 times 5.97 E24. And we're divided by 6.37 E6 plus 8848. So it's about minus 5.3 times 10 to the 9th joules.